Welcome to this next video in the playlist on group theory. In this video, what we're going to define is the concept of a characteristic subgroup. Okay, and we will see that characteristic subgroups are really stronger versions of normal subgroups. So being a characteristic subgroup, the condition for that is just a stronger version of being a normal subgroup. Okay, and you'll understand what I mean by that by the end of this video. Okay, so firstly then let's just do the setup. So we're going to be working with some group capital G, and this is some arbitrary general group. It doesn't need to be anything special. Okay, it can be finite or infinite, it can be abelian or non-abelian. It's just a general group capital G, and we are going to see what a characteristic subgroup of this general group is going to be, what the definition of that is going to be. Now, before we can actually discuss this, before we can actually define the notion of a characteristic subgroup, there's some prerequisites that I'd like to go over before we do that, and the prerequisite that I'd like to go over is the concept of an automorphism, just reminding you of the concept of an automorphism. We have had videos previous to this in the playlist on group theory on automorphisms, but because the concept is so central here, I want to just remind you of it. Okay, so what we're going to talk about then is automorphisms initially, and then once we've discussed automorphisms, we'll define what a characteristic subgroup is. Okay, right, so automorphisms. So remember, an automorphism is a special type of isomorphism where the domain and codomain group are the same thing. Okay, so an automorphism is a mapping, which I'll call phi, so here is the automorphism, from the group to itself that is an isomorphism. Okay, and remember what this means is that the mapping must be bijective, that's the first condition. Okay, so one to one and onto, injective and surjective, and it must also be compatible with the composition laws on the domain and codomain group, which in this case, of course, is the same composition law. Okay, so for all A and B that you can possibly dream up from the domain group, okay, so from G here, it must be the case that if you take phi of A composed with B, that it's equal to phi of A composed with phi of B. Okay, so on the left-hand side, you're firstly composing the two elements together in the domain group, and then mapping the answer into the codomain group. And on the right-hand side, what you're doing is firstly mapping both elements that you want to compose into the codomain group. You're taking phi of A and phi of B here, and then you're composing them together in the codomain group. And because our domain and codomain in this case are the same thing, those two compositions are exactly the same. So I won't color code the compositions as I usually do in the case of talking about isomorphisms or homomorphisms, because the composition is in the same group. Okay, now, let me then remind you of the interpretation of this, because yes, this is the rigorous definition of it, but what does this really mean? And this really does capture a really important concept. Okay, so let's just draw a picture of our group capital G. So fundamentally, remember, our group capital G is just a set of symbols, so let's say here is the set of symbols, with a composition law defined on it. So I'll draw my composition table here, and we've called our composition abstract composition here. So here is our group, it's a set of symbols, and of course just to put something in that set, I'll put the identity element, it will have that always, so I'll put that in there just to make the set look non-empty. Okay, and then we've got our composition table over here, where of course we've got every single element of the group given a row and every single element of the group given a column, and that tells us, that defines what any element composed with any other element is going to be. Okay, so what then is the interpretation of a group automorphism then? Well, the idea is this, that it captures, and this is the sort of one-line way of stating what a group automorphism is, it captures an algebraic symmetry in the structure of the group. Okay, now let me make that more precise. So this is a bijective mapping. Okay, it's going to take every element of the group here, every element in the set, and it's going to map it onto another element of the group. And that mapping is going to be a set permutation. Okay, it's going to be injective, so every element in the group only gets one element of the group being mapped onto it. Every element of the group gets a unique thing to be mapped onto. And it's also going to be surjective, so every element of the group is going to be hit. So you're truly just going to be permuting the elements here. Okay, so what you can imagine doing is taking out your little eraser and erasing each of these elements one by one and replacing them with a new symbol, a new element of the group. Okay, that's really what you're doing here. Of course, the identity we know is always mapped onto the identity, so you don't need to bother rubbing that one out and replacing it with some new symbol. But some of the others might be moved. Okay, and you'll go along and rub them out and replace them with their new symbol. Okay, that's what this is really capturing with the bijective portion. And now here's the incredible bit. What does this mean? What does this compatibility rule mean? Well, this means that if you now turn your attention to the composition table and again pull out your eraser and start erasing all the entries in this composition table, starting with the headings. Okay, so start by replacing the titles for the rows and the titles for the columns. So go through each of the titles for the rows and each of the titles for the columns, rub them out and replace them with their new symbol. Okay, and then do the same for all of the entries of this composition table. Go through every single entry and then rub it out and replace it with its new symbol under this mapping. And what this rule says, the intuitive thing that this rule says, is that when you do that, the composition table you end up with after you've rubbed everything out and replaced it with what this mapping maps it onto will be the same as the original composition table. Okay, yes, the answers might have moved around a bit. Okay, so if you want to compose two things together, you might have to go to a different slot on the composition table, but that doesn't matter, that doesn't mean anything. Okay, the actual answers, if you take any two elements of the group and compose them together, before you had rubbed it out and replaced the composition table, you would get the exact same answer as afterwards. Okay, so the composition tables truly are the same, and that is what this property says. Okay, so it really shows you which elements of the group are effectively equivalent algebraically. That's what a group automorphism is going to do. It's going to map elements of the group onto other elements of the group which are algebraically equivalent to them. Okay, so effectively they might be two different elements of the group, but they're not that different at all. They're algebraically identical, and in fact if you swap them round, if you change the symbols, swap their symbols around, you wouldn't know the difference. Okay, the group looks identical. So it really truly is about algebraic symmetries of a group. So group automorphisms capture algebraic symmetries of a group, and that intuitively is why a group automorphism must always map the identity element onto the identity element, because the identity is the only element with those incredible algebraic properties. Okay, so there are no other elements of the group that are equivalent to the identity but just have a different symbol. Okay, right, so there's a reminder of group automorphisms. Now, before we actually go on to defining what a characteristic subgroup is then, let me remind you of the group of automorphisms for a group. Okay, so what we can do then is we can go through our group here. So we've got some group. We can work out, we can find, in principle at least, we can find all of the automorphisms for this group. Okay, so every group will always have one automorphism, which is the trivial automorphism, which is just the identity map. That will always be a group automorphism, but hopefully you might have a few more interesting ones. And what you can do is you can collect these maps together into a set, and we call this set the set of automorphisms of G, like so. And in fact, this forms a group under composition, okay, because you can compose two elements together by defining the composition law just to be compose the two automorphisms together, and the overall mapping, the composite mapping, will still be an automorphism. Okay, and that composition law obeys the axioms of a group when put onto this set. Okay, so we talk therefore about the automorphism group of a group. Okay, and that's how we denote it, aut G. Okay, so the set of all automorphisms of G forms a group which we call this. Now, remember there is an important subgroup of this, which is the set of all inner automorphisms of G, which we denote in I-double-N for inner, and then G. So the inner automorphisms of G, which is going to be a subgroup of the group of automorphisms of G. Now, this subgroup is going to be the subgroup that contains all of the inner automorphisms of G. Now, what is an inner automorphism of G? Well, an inner automorphism of G is an automorphism that you can interpret as being the mapping that you would get if you conjugated the entire group by a certain element of the group. Okay? So in the videos on automorphisms earlier in the playlist, what we discussed is that if you take an arbitrary element of the group, so let's take an arbitrary little g as an element of the group, what you can do is conjugate the entire group by that element. And what that means is you go through every single element of the group and you conjugate it by little g. Okay, and this will map the entire group onto G. This is a bijective mapping of the elements of G onto other elements of G. Okay, and this actually is a group automorphism. It does obey this compatibility property here. Okay, and such automorphisms that can be interpreted as all you're doing is conjugating all elements by a certain element of the group are called inner automorphisms. So what you can do to find all of the inner automorphisms is just go through every single element of the group, conjugate every other element of the group by that element of the group, and form a mapping from that. Okay, so let me just make this explicit. So for all little g is an element of capital G, what you can form is an automorphism which we'll call phi sub g, which just maps every element of the group, which I'll denote A now, onto GA, G inverse, and that's going to be a mapping from capital G to capital G, and it actually is going to be a bijective mapping, and it will obey compatibility of the composition law. Okay, so it does form an automorphism, and if you go through all little g as an element of capital G and form these mappings, that forms you the set of all inner automorphisms of G. Now, of course, not all of the elements of G are necessarily going to have distinct inner automorphisms attached to them. Some of them might generate the exact same inner automorphism, so you're not necessarily going to end up with a separate inner automorphism for every element of the group. And in fact, if you're working in an abelian group, of course, it's really trivial. The only inner automorphism is going to be the identity automorphism, because conjugation has absolutely no effect in an abelian group. Okay, but often in non-abelian groups this can be far more interesting. Okay, the other important thing to say is that usually there are other automorphisms of the group that are not inner automorphisms of the group. So usually this is a proper subgroup of this. So not all of the automorphisms of G are necessarily inner automorphisms of G. Okay, but it's a nice, easy to find set of automorphisms of G. I hope you all agree that, constructing this is quite difficult, but constructing this is extremely easy. Okay, you just go through every single element of the group and use each one of them to conjugate the entire group and collect those mappings that are distinct together, and you've got the set of all inner automorphisms of G. Okay, so there's a reminder of what inner automorphisms of G are and what automorphisms of G are. The final little prerequisite thing that I want to point out is that if you have a subgroup of your group, okay, so final thing before we actually define what a characteristic subgroup is, if we have a subgroup of the group, so let's say H is a subgroup of G, and let's say we have some automorphism of G, so let's say phi is an element of the set of automorphisms of G, or the group of automorphisms of G. Okay, my claim is that if we act phi on the subgroup G, on the subgroup H, of course, phi acts on the entire group capital G and maps every single element of capital G onto another element of G. Okay, so it will certainly act on all of the elements of this subgroup capital H and map them onto some other elements in G. Okay, so what we can consider is what is the image of the subgroup H under the mapping phi, and I'll denote this phi of capital H here. Okay, and my claim is that that will still be a subgroup of G, and that, of course, I could do a proof of this, but I hope I don't need to. I hope intuitively, from your intuitive understanding of the fact that an automorphism is this special type of isomorphism from a group to itself, that you will understand why this has to be true. Okay, so let me give you the argument then. So H is a subgroup of G. Okay, what we can imagine doing is restricting our automorphism of G down just to H. So we're now just considering it mapping H onto a subset of G. So let me just draw a little picture for this. So here is our entire group, capital G, and of course we'll have our codomain here as well, which is the exact same thing. So here's our mapping phi, here's G once, and here's G again, and I'll just colour it in here. So we'll have G like so, in orange. Okay, now let me mark on H in the domain group. So here, let's say this is the subgroup H in the domain group. And now what I'm considering doing is just restricting my attention to H. Throw away the rest of G. I don't care about that. Just restrict your attention down to H. Okay, all of these elements are going to be mapped onto some elements of G. So let's just draw it out here. So let's say this is phi of H. And I don't mean to imply that it's necessarily the exact same subgroup here, or subset rather. It's just a picture, so don't interpret this as it's mapping H exactly onto itself. I should have drawn it slightly differently maybe, but too late now. Okay, so here is phi of H in red here, and of course this will still be a bijective map. Okay, because phi is a bijective map from G to G. Okay, so it's injective and it's surjective. This, by definition, is all of the things that H are mapped onto. So it's certainly a surjective map, and it will also be injective because it inherits that from the larger map. So the mapping from H to phi of H is going to be a bijective map. It's also still going to obey this compatibility of the composition law, okay? Because if it didn't obey it on this subset of G, then it wouldn't obey it on the entire G. Okay, so if it obeys it on the entire of G, then it certainly obeys it for a subset of G, which is H. So this little map where we've now restricted our attention from the green place to the red place, this is going to be a bijective map with the compatibility of composition. So of course it's going to be an isomorphism between this and this. Okay, so truly therefore this structure over here, phi of H, must be isomorphic to this, and therefore it must be a subgroup of G, it must be a group in its own right. Okay, so here's the claim that actually when you take phi of a subgroup of your group, so if H is a subgroup of your group, and you take phi of that, you take the image of that, you are going to end up with another subgroup of G that is isomorphic to your initial subgroup. So phi of H here will be isomorphic to the initial subgroup, but it's not necessarily the same as the initial subgroup. Okay, it could have changed, but it is still going to be isomorphic. So any subgroup is going to be mapped onto another subgroup that is isomorphic to that initial subgroup. And as I say, I could prove that more rigorously, but I hope your intuitive understanding of the fact that this is truly an algebraic symmetry, this map, leads you to believe that that is true. Okay, so that's really important for us in our definition of a characteristic subgroup, that an automorphism will always map a subgroup onto another subgroup of that group, which is isomorphic to the initial one. Okay, so now let's actually define what a characteristic subgroup is. Okay, so a characteristic subgroup, first and foremostly, it is just a subgroup of G. So H is a subgroup of G, and if we want to elevate its stature up to being a characteristic subgroup, then this is written like so. H is a characteristic subgroup of G, okay, like so. So H, CHAR is a characteristic subgroup of G, okay, and of course, to be this, it has to be a subgroup of G, so this is one criterion, of course, and then the new criterion, here's the interesting criterion, is that it has to have the property that for all automorphisms of the larger group capital G, this subgroup capital H is fixed by every single one. So let me write this out. So for all phi, which is an element of the group of automorphisms of G, so you pick any automorphism you like of G, when you act phi on the subgroup H, okay, you take the image of H under this automorphism phi, you must get the same subgroup back. you must get H back. Now that does not necessarily mean that phi fixes every single element of the subgroup H. It means that when it actually acts on all of these elements of the subgroup H, it maps them onto other elements of the subgroup H, and this actually forms a bijective map from H to H, so indeed an automorphism of the subgroup H. But the point is that it doesn't map H onto some other subgroup of G that is isomorphic to H. Okay, it maps it onto the same subgroup, which is of course isomorphic to the initial one. Okay, right, so that is the condition, that it is fixed by all automorphisms of the group capital G. Now, just before we have a break, let me explain why this is a stronger version of being a normal subgroup. What did it mean for H to be a normal subgroup of G? So let's now say H is a normal subgroup of G. Well, remember that meant that you were a subgroup of G, firstly, but then the interesting criterion was that if you took any other element of the group, so for all little g is an element of the group capital G, if you use that to conjugate the normal subgroup, GH, G inverse, it had to give H back again. Now let's write that in a way that we have never written it before, because look at what we're saying here. We are conjugating H by this element G. That is an inner automorphism of the group capital G. So effectively the normal criterion, although we've never written it in this way before, effectively the normal criterion is saying that for all automorphisms which are inner automorphisms of G, okay, if you act that inner automorphism on H, you must get H back again. That's another way of writing the criterion for being normal. We've never written it in that way before in this playlist, but that is another way, and that's a helpful way of writing it to see the parallels with this. This is a stronger version of this. In normal, we're just saying that this subgroup has to be fixed by any inner automorphism of the group capital G. So you come up with any inner automorphism, which means a mapping that is effectively equivalent to just conjugating all the elements of the group by a certain fixed element of the group. Okay, and H must be fixed by every single one of them, i.e. mapped completely onto itself. However, with saying that H is a characteristic subgroup of G, we go stronger, we go one step up. You pick any automorphism you like from G, not necessarily just an inner automorphism of G, then H is fixed by that automorphism of G. Okay, so clearly, if H is characteristic in G, then it is also normal in G. But it's not true the other way around to say that if H is normal in G, H is characteristic in G, because there could be automorphisms of G that are not inner automorphisms, and you don't know just from knowing that it's a normal subgroup of G that it's fixed by those automorphisms which aren't inner automorphisms. But certainly, if it's characteristic in G, you can instantly conclude that it is normal in G. So this is our first little statement here, and that really is why I said right at the start that being a characteristic subgroup of G was a stronger version of being a normal subgroup of G. Okay, so we'll have a break here, and in the next video we'll take this discussion a little bit further.